Welcome to Lecture 4, which we're going to take those motion concepts we worked with in Lecture 3 and use them to actually predict future motion. And before I get into the math of doing that, let me point out that there's a real philosophical issue here. And the philosophical issue is inherent in Newtonian mechanics, and that's the idea of the so-called clockwork universe. If we understand motion well, then we understand how to predict future motion. And doesn't that mean that all future motion is determined? This is an idea of determinism that seems to be built deeply into Newtonian physics. Of course, we know that Newtonian physics is not really a completely accurate description of reality, so that's no longer a deep philosophical issue, but it was in Newton's time. Newtonian physics seems to be predicting a universe that unwinds like a giant clockwork. It's completely determined by whatever the initial conditions are. And in the simple exercises we'll do in this lecture, you'll see how that plays out using Newtonian concepts of motion. We're going to deal with a very important special case, a special case that's easy to work with, and that's the case of motion with constant acceleration. It's the only case we'll deal with in this course. Motion with non-constant acceleration is more difficult, and that generally takes calculus. So let's plunge right in and look at some of the details of this. So here are some graphs that we saw last time, graphs of position, velocity, and acceleration. In this case, the rate of change of the velocity varied. The velocity was rising at the beginning. It was falling later on. The rate of change of velocity was varying, and consequently, the acceleration in that case was not constant. Here are three other graphs of position, velocity, and acceleration, again versus time. They're a little bit less complicated than the ones on the left that we looked at in Lecture 3. So let's look at these. Here we have the velocity. It's represented by the slope of this line, the velocity as a function of position, as a function of time. And you can see that in any place along those lines, if you drew a little line that was representing that slope, it would be the same. And consequently, the velocity is changing at a constant rate. The velocity is increasing, but it's increasing at the constant rate. In every second, it increases by the same amount. And that means the acceleration is constant. And that's the case we're going to deal with in this lecture. That's the case that is easy to deal with mathematically without having to resort to calculus. So that's what we'll be doing here. So let's begin by looking at how we predict the velocity of an object which is undergoing constant acceleration. So here's a statement of what's going on. At some time, which we'll call t equals 0, our starting time, an object has some velocity which we'll call v sub 0, or I'm just going to say that v naught. That sub 0 is a standard mathematical way of writing a starting condition, sub 0, the initial condition. So at time t equals 0, the object has velocity v naught, and it moves with constant acceleration, which is a. I don't need to put a sub 0 on the a because the acceleration is constant. It's the same at all times. So what's its velocity at any later time? So let's start with a graph of velocity versus time. It starts out at v naught. So at time t equals 0, at the place where the two axes meet, the velocity is v naught. It then rises steadily because the acceleration is a constant. The slope of this rise is the acceleration, because acceleration is the change in velocity divided by the time interval, delta v over delta t. Let's take a look at that. Here's some time t. We started out at time t 0. We look at some later time. There's a time interval t over which the velocity changed from v naught to some final value v. Now, what is that change? Well, that change is the acceleration times the time, because acceleration is the rate of change of velocity. And I can say that very clearly in this case because I've specified that the acceleration is constant. So now we're at velocity v. We started out at velocity v naught. We've undergone a change, at. So we can write that velocity v is velocity v naught, where we started, plus that change, at. Here I explicitly wrote the time sign, but in general I'm not going to do that. I'm going to adopt the mathematical convention that when two symbols are written next to each other, multiplication is implied. So we have now our prediction of the velocity at a future time. It's the starting velocity plus this change in velocity caused by the constant acceleration. Let me ask another question now. What's the average velocity of this object between time 0 and time t? Well, I think you can see in this case the average velocity is halfway in between the two. Why is that? It's because the object spent half the time going at speeds below its average halfway in between, and half the time going at speeds greater, and those speeds were increasing uniformly on either of those intervals. So the average velocity in the case of constant acceleration is just half the starting velocity plus the final velocity. That is not necessarily true if the acceleration isn't constant. So v average, here it is a half v naught plus v in that case. And that's going to be an important result for us to use. I just want to emphasize, though, that that's true only for constant acceleration. Students get in big trouble when they try to apply constant acceleration formulas to accelerations that aren't constant. Here's a case where the velocity was close to v naught for a long time. In other words, the object wasn't accelerating much, and then it accelerated rapidly to higher velocities. And in that case, the average is going to be much closer to that initial velocity. It's not going to be halfway in between. It's less than a half v naught plus v. Here's a case where the opposite occurs. It accelerates rapidly at first, and then the acceleration levels off, and the velocity is mostly near the upper limit. And so again, the average is not half the initial plus the final. It's not the average of the initial and the final. In fact, it's greater in that case. So let's continue now and raise the question of how do we get to the position of the object as a function of time now that we've gotten its velocity? So we're going to predict position. Same situation. At time t equals 0, we've got an object at some position, which I'll now call x naught. That's its initial position. It has this initial velocity v naught we've just talked about. It's going to move with a constant acceleration a, and we want to predict its position at any future time. The clockwork universe idea. We want to predict what it's doing. And that's enough. What's written there in that English statement, that's enough to tell us where the object is at any future time as long as its acceleration remains constant. So let's remember, the average velocity is the rate of change of position, delta x over delta t. I can solve that algebraically for delta x just by multiplying through by the delta t, and I have delta x as v average times delta t. Delta t in this case is just t. That's not always true, but it's true in this case because my starting time I called time 0. So delta t is t, time I end up at, minus my starting time, 0. T minus 0 is just t. So v average delta t becomes just v average times t. So now I can write x. X is where I started out, plus whatever change occurred in my position, delta x, and I've calculated that change. It's v average times t. So my position is x sub 0, where I started, plus v average times t. Pretty straightforward so far. But I know that v average is a half v naught plus v, so I can write that x is my initial position plus my v average, this term, times t. Let's go from there now to try to predict exactly where this object will be at some future time. So here's the result we just had. My position is my initial position plus my average velocity, the average of the initial and final velocities times the time. But we already know what the velocity is at any given time. We worked that out before. It's the initial velocity plus the acceleration times the time. So I'm going to take this expression for v and put it in here. So I'm going to get this equation now with this expression in for v. X is my initial x plus a half v naught plus v plus at. There's the second v naught coming from there. There's the at, and the whole thing is multiplied by t. Multiply this all out. I've got two v naughts in there. The half kills off the 2, but the half stays there in front of the a times t, and I end up with my position as a function of time. My initial position plus a position that increases because of the initial velocity, plus an extra term that reflects the effect of the acceleration. Let's take a closer look at that equation. Here's my anatomy of the equation that gives position as a function of time in the case of constant acceleration. And we have here a graph that shows what's going on. So what I have here is the initial position x naught. Here's position as a function of time. If nothing else happened, if there were no initial velocity and no acceleration, the object's position at time t would remain constant at that initial position. But there is an initial velocity, and even if the object weren't accelerating, its position would change because of that initial velocity, and if it weren't accelerating, it would change at a constant rate. That's the slope of this line, v naught. So this interval, v naught times t, is the change in position due just to the initial velocity. displacement being change in position. And finally, there's this extra term due to the extra velocity that's resulting from the acceleration. And that, interestingly, goes as the square of the time. We saw that last time when we developed this equation. So that goes as the square, and this curve, therefore, goes up in a typical quadratic fashion of curves that have something depending on the square of some other variable. So there is an anatomy of the equation that describes the position of an object moving in one dimension as a function of time. That is the equation that gives us, in a sense, the clockwork universe for a case of constant acceleration. Let's do an example of that using this equation to see how it works. I've got an airplane. It's got to make an emergency landing at a small airport. The runway is only 900 meters long. And it touches down at 80 meters per second. That's its touchdown speed. That's the speed it's moving when it hits the runway. And then it decelerates at a constant 4 meters per second squared. By that I mean it is accelerating but slowing down. The acceleration is opposite the direction of its velocity. And the question is, will it stop before the end of the runway? So this is a real question about a real-world situation that you would like to know the answer to if you were sitting on that airplane or if you were the pilot. So we've got to sort of set up the problem first. So let's take our time 0 to be the time when the interesting stuff starts to happen, and that's when the plane touches down. So t equals 0 at the instant of touchdown. We can take t equals 0 anytime we want, but in this problem, it's convenient to take it at the instant the plane touches down. And let's call that position x equals 0. Just makes the math easier. I could have called it x equals 5 miles or whatever I wanted, but I'm going to call it 0 because it's going to make the math a little easier to work with, because then this quantity x naught that appeared in our equation, the initial position, is 0. And let's take the positive direction to be the direction toward the end of the runway, the direction the plane is going. I could have made it the negative direction. Didn't matter. But this is going to make it just a little easier to think about. Then our initial conditions for this problem are v naught is plus 80 meters per second, plus because the plane is going in the direction I defined to be the positive direction, but its acceleration is minus 4 meters per second squared. The acceleration is opposite the velocity, indicating the speed is decreasing, the plane is slowing down. So now we've set up our problem. So here we are, x naught is 0, v naught is 80 meters per second, and a is minus 4 meters per second squared. The first question, how long will it take the plane to stop? Well, that's a question about what will be the time when v is 0, when the velocity has decreased to 0. We know that the velocity with constant acceleration is the starting velocity plus the acceleration times time. I can solve that for time, which is what I'm interested in here, by pulling, let's see, I want v to be 0, so that's going to be 0, and I can pull v to the other side. It becomes minus v naught, and then I'm going to divide by a. And so t is minus v naught over a, and if I work the numbers, that's minus 80 meters per second, because it's minus v naught, divided by a, which is minus 4 meters per second squared. The minus signs cancel, and it's going to take 20 seconds for the plane to stop. That isn't the answer to our question. We want to know how far it's going to go in that 20 seconds. So here we are again with our initial conditions, and the result we just found that it's going to take 20 seconds to come to a stop. So the next question is, how far will it get in this time? So here again is our equation for position as a function of time. We know that x naught is 0, we know that v naught is 80 meters per second, and we know that the time is 20 seconds. So we can plug those things in and find out what x will be. X will be where the plane is when its velocity has reached 0, that is when it's come to a stop. 80 meters per second times 20 seconds plus a half times 4 times 20, and if you work out the math, that's 800 meters, and the plane is safe by 100 meters, about 300 feet. So there is a practical example of using the equations of constant acceleration to work out the results of an important problem, at least important to you if you're on that plane. Okay, so far we've sort of talked about objects that were moving, I sort of implied horizontally. I showed this example has an airplane moving horizontally along the runway. But there's a very important special case of constant acceleration, and that's the acceleration near Earth's surface due to gravity. So let's talk about that acceleration a bit. It turns out that the value of the acceleration due to gravity near Earth's surface, the acceleration with which an object that's dropped falls, is about 10 meters per second every second. It's a little closer to 9.8 meters per second per second. 9.8 meters per second squared. In the English system, that's about 32 feet per second per second. It varies on other planets. That's what it happens to be on Earth because of Earth's mass and Earth's radius. And in saying that that acceleration is constant, I'm making two approximations, neither of which is perfectly true. First of all, I'm neglecting air resistance. And that's a good approximation for objects, sort of like my tennis ball. It'd be better for a baseball, that are fairly compact and massive. It would certainly not be a good approximation if I dropped a piece of paper or a ping pong ball where air resistance would be more significant. The more profound approximation is that to say the acceleration of gravity near Earth's surface is constant is to neglect the curvature of our planet. The acceleration of gravity actually changes with position, with height, and we'll understand that more when we get to our lecture on gravity. But for now, as long as we remain near the surface of the Earth, don't go very far compared to the Earth's radius, it's approximately true that the acceleration of gravity is approximately constant and with a value of about 9.8 meters per second squared. Being in the state where the only force acting on you is gravity, and so you're experiencing gravity's acceleration, is called the state of free fall. And I want to emphasize that free fall doesn't necessarily mean falling downward. When I throw that ball up, as soon as it leaves my hand, it's subject only to the acceleration of gravity. So even as it's going up, it's accelerating downward with acceleration 9.8 meters per second squared. Let's do a real-world demonstration to understand the acceleration of gravity. Okay, so here we are in our laboratory. We're using the same piece of equipment we used in the previous lecture. It's that motion sensor that works like the device in your camera. It's now pointing straight down. And what I propose to do is drop an object from here. We'll be recording distance going positive downward. And we'll look this time at the position, the velocity, and the acceleration. I didn't look at the acceleration last time because it was somebody pushing a chair. Tiny little variations in velocity lead to great big accelerations, and it really doesn't look very pretty. This is going to be a much smoother thing. We're going to really see the acceleration being essentially constant. Again, this is the real world. It won't be perfect. By the way, I should mention that a lot of the demonstration equipment you're seeing in this course is provided courtesy of Pasco Scientific, a company that makes educational physics, particularly equipment, and that's what we'll be using a lot of in this course, so we're very grateful for that. So let me begin the experiment. Here again is our graph. We're going to have three quantities plotted this time: position, velocity, and acceleration. Each of them has a different scale. They're going to appear simultaneously on this graph when I do the experiment. I've got the experimental apparatus set so that when I let go of the ball, it's got to fall a certain distance, a fraction of a meter, before it starts recording data. The reason for that is removing my hand from the ball is kind of a tricky process. Did I accidentally throw it up in the air a little bit? Did I move it sideways? I might get some spurious readings, particularly for the acceleration at that case. So I'm going to remove my hand from it and let it fall. And then when it gets about this far from the sensor will start taking data, and the sensor will automatically stop when it gets a little bit above the floor. So that's going to be the experiment. A lot of lead into it, but it's going to be over in a very short time. So here we go. I'll start the computer, and the data will start taking as soon as the ball drops below a certain point. So here we go. Okay, let's look at what we've got. Each run is a little bit different, but they're quite remarkably consistent. The red curve is position as a function of time. It's beautifully smooth. It shows that upward trend associated with that dependence on the square of time. This is time going along the horizontal axis. The red is position on the vertical axis, and beautifully smooth position as a function of time curve. What's the velocity that corresponds to that? It's the slope of this curve at every point, and that's the green curve. And the green curve is running from, about starting at 1.5 meters per second up to about 4.5 meters per second. The velocity has increased. And the fact that that green line is pretty much a straight line, it's not perfect, because this is the real world. There are other effects. There's air resistance. The ball may be wobbling a little bit. The place that the ultrasound beam hits the ball may be slightly different. All these things make the experiment less than perfect. But it's pretty close to a straight upward line, and that tells us the acceleration is fairly constant. And here is the acceleration as a function of time. You might say, well, that's not constant, but look at the scale. It ranges from minus 10 meters per second squared up to 16 meters per second squared up there. And in that context, it's occupying a pretty narrow range between about 8 and 10 meters per second squared, pretty close to the 9.8 meters per second squared that we know to be the acceleration due to gravity at Earth's surface. So even though this line looks a little bit jagged, it's still telling us the acceleration is on the order of 10 meters per second squared, and it isn't changing a whole lot. You can see this sort of downward glitch in the acceleration is probably associated with a pair of points here where the velocity looks like it's gotten a little bit lower. That may be some effect of how the instrument was taking the data. By the way, the instrument is taking data about every tenth of a second, so it's about intervals like this are the delta t's we're using to take the data. It isn't taking data continuously. That's another source of error because it means we aren't truly getting instantaneous readings. But again, if you think about this graph in the context of that anatomy of the equation, where we saw the terms due to the three parts that led to the velocity rising because of the acceleration, and that led to the position going up quadratically. That curve beautifully reproduces that result. These don't reproduce it quite as beautifully, but they're still nice verifications that we've got essentially constant acceleration, velocity rising linearly with time uniformly, and position rising quadratically with time. Okay, let's move on and look a little bit more mathematically at how we would describe the situation of free fall and acceleration due to gravity. So let's think about how we would describe the motion of an object under the influence of Earth's gravity. That is, this free fall with constant acceleration downward 9.8 meters per second squared. The first thing we need to do, as with any problem involving motion, is to establish a coordinate system that tells us where our starting point is and enables us to measure positions in different directions from that origin. So in this case, we have one-dimensional motion. It's along now a vertical line, up or down. And so we're going to establish a vertical line as our coordinate system. And we can establish the zero of position anywhere. Now, just out of convention, because we're going to be dealing soon with two dimensions, horizontal and vertical simultaneously, we're going to call this case of one-dimensional motion, we're going to call the position y rather than x. Because when we go to two-dimensional motion, we'll reserve x for horizontal and y for vertical. There is nothing magic about that. I could have called the vertical position x or z or anything I wanted, but I'm going to call it y. So I'm going to take y equals 0 at the ground. So here I show a picture of our coordinate system. Y equals 0 is at the ground, or maybe the floor, or maybe the initial position of some object. It didn't have to be. I could have put y equals 0 on the top of a table. I could have put y equals 0 at the top of the building, and then negative y's would have been downward. It doesn't matter. That's just a human artifact. I'm going to define the downward direction as negative. It kind of makes sense. The upward direction is positive. It didn't have to be that way. In fact, when I did the demonstration, I defined the positive direction as downward because I was measuring distance from my motion sensor, which was watching the ball fall. But now I'm going to talk about up as being positive, down as being negative, and I've established y equals 0 at some appropriate point, like the floor in this room, for example. So then the question is, what are the equations that describe the motion of an object undergoing free fall under the influence of gravity alone? Well, they're the same equations we just derived. They're the equations that describe the motion of a system subject to constant acceleration in one dimension. The difference is the acceleration in this case, given our coordinate system with the upward direction positive, the acceleration is minus g. Now let me make that a little bit clearer. The number g stands for the number 9.8 meters per second, a positive number intrinsically. We want to put a direction on it. That depends on our coordinate system. In a coordinate system with the positive direction upward, then the acceleration that enters our equations is negative because it's opposite the positive direction. So in my coordinate system with these conventions, the acceleration is minus g. The velocity is its initial value plus the acceleration times time, but because the acceleration is minus g, that becomes v equals v sub naught, the initial velocity, minus g times t. And then the position, that same equation we worked with before, becomes y is the initial y position plus the initial velocity times the time minus, because the acceleration is negative, a half gt squared. So there are the three equations that are governing the motion of this object under the influence of gravity alone. Constant acceleration, value minus g in our coordinate system, velocity that, if you will, decreases linearly with time because the acceleration is negative, and a position described by this more complicated equation, again, quadratic in time. So that's how we're going to describe free fall. Those are the equations of motion describing free fall. And I'd like to do one example of that, which is a little bit more complicated than our airliner landing example. So let me begin with a simple demonstration. I want to take a ball, and I want to start with it at some point in my hand, and I want to toss it straight up in the air and get out of the way. And I want to ask the question, when is that ball going to hit the floor? So I'm going to toss the ball straight up. I'm going to know the height at which I tossed it. I'm going to know the speed with which I toss it up. And I want to ask the question, when does it hit the ground again? Or when does it hit the ground? So let's take a look at the mathematics of that. So here's our ball toss. So we toss a ball straight up. Let me put some numbers in. It leaves your hand 1.5 meters above the ground. It's moving at 7.3 meters per second. And the question is, when does it hit the ground? Well, let's take y equals 0 at the ground. That seems to make sense. Again, perfectly arbitrary, but we'll do that. So y naught is now 1.5 meters because I tossed it 1.5 meters above the ground. Now, I might have said, why didn't I take y naught equals 0 here? Well, I could have, but then I would have had a harder time expressing the final state because the final state is I want it to be at the ground. The v naught is 7.3 meters per second because that's the speed it was moving at when it left the hand. Here's the equation of motion for the position. Y is the initial y position plus this term associated with the initial velocity and then this negative term associated with the acceleration. That already tells us that what's going to happen when the ball leaves my hand is it's first going to go upward because of this term. But as time advances, this term is going to get bigger and bigger because time is squared in it, and eventually that's going to make the position reach a maximum, and then it's going to start going down again. We can just see that looking at the equation. Let's solve it, though. Let's do the real math of it. So we know y, we know y naught, we know g, and we need to solve for the time t when y is 0. And that's not quite as trivial as some of the other equations we've worked with. Here's our equation. Y is y naught plus v naught t plus a half gt squared. We know y, we know y naught, and we know g. We've got to solve for t. So I'll put 0 for y because that's what we want to know. When is it going to be on the ground? When is y going to be 0? Let's do the math. Well, back in high school, you learned how to solve equations like that. Those equations are called quadratic equations because the unknown, in this case the time t, appears squared. And I'm not going to go through all the math of doing the quadratic formula, but there was a formula, a general formula for equations of this form, some number times x squared plus some number times x plus some number alone equals 0. That's what I've got here. The first number a is minus a half g, the second number is v naught, the third number is y naught, and there's the solution from the quadratic formula that you learned. And the interesting thing about that solution is it's got two possible answers. That's what the plus and minus signs indicate. And if we do the math for this problem with the numbers we had, we get either minus 0.18 seconds or 1.7 seconds. Why are there two answers? Which is the right answer? Well, before we throw away the answer that maybe looks odd, the negative answer, let me just point out that in 1928, the famous physicist Paul Dirac had a similar problem. He was working with Einstein's relativity theory. He came up with a negative square root. He said, I'm not going to throw this out. And as a result, he realized there had to be what's called antimatter. We'll get to that in the last part of the last segment of the course. And he got the Nobel Prize for that in 1933. So don't throw out answers that look odd. Think about what they mean. And we'll think about that too, because another way of looking at this is to look at the problem graphically. So let's get some insights into why there are two answers and what's going on with this graphical approach. So here's a graph of time on the horizontal axis, position, vertical position on the vertical axis. We're going to start out at time t equals 0 at 1.5 meters. So there goes our ball. It describes position versus time, this nice parabolic shape. This is not the shape of the trajectory. I threw it straight up and it came straight down. But this is the position versus time graph. And at our final answer, 1.7 seconds, that's when it hit the ground. The curve continues because the curve doesn't know about the ground. The curve says if the acceleration had continued constant due to gravity, we would have just gone like this. It didn't continue constant because the floor exerted forces and the acceleration changed. But here's the interesting part. If we continue this curve back in time from before when we threw the ball would have been on the ground at t equals minus 0.18 seconds. The equations thought, if I can imbue them with thought, they thought that the acceleration had always been constant and was always going to be constant. Hence, they thought the ball left the ground and it if I had thrown the ball from the ground 0.18 seconds earlier with the appropriate speed it has there, which is not the 7.3 meters per second, but something faster, it would have described the same trajectory again. It would have followed the same path, but going a little bit more of it. So that's a graphical approach telling us what's going on there. That's a fairly complex problem in acceleration, in motion with constant acceleration. Okay. Well, let me end by just summarizing what we've learned today about motion with constant acceleration. First of all, with constant acceleration, there are simple algebraic equations that describe velocity and position as functions of time. The acceleration is constant, the velocity is linear in time, and the position changes as the square of time. And a very important case of constant acceleration is the case of free fall under the influence of gravity near Earth's surface.